morning. We are continuing double integration. We're looking at general regions, correct?
Yeah.
Okay, that's right. Yeah, we left off here. Now we at least picked the region, right? I believe I asked you to try and describe it at home. What did we come up with?
Zero to the x equal to 8x less than or equal to 8. Region.
And what about y? Again, your imaginary bar, right? I agree, it's going to totally slide over to 0 to 8. But what is it going to do for y? And so the sliding right now is doing what? From the blue to the pink? Uh-oh. What happened? It's now the blue to the green, isn't it? No, that means we have two regions. Are we lucky enough to maybe do vertically? We can use one region. So instead we do horizontally simple. Y is going to slide up from 0 to 4, right? That's what? Pink to the yellow? Oh no. Then pink to green. Looks like it doesn't matter. Whether we do vertically simple or horizontally simple, we're going to have a union of regions. So what I'm going to do is stick with vertically simple. Region divides right there. That is at x equals 4. How would you figure that out algebraically? Is that you determine that point of intersection? What's this paint? What curve is that? What curve is that?
Line 25
What's the green?
X equals 16.
What has to be true at their point of intersection?
They're equal.
They're the same, right? X squared equals 16. So X has to be 4. And so for D1, we're going 0 to 4 for X. And over that region, the upper bound is X. And D2, X is going from 4 to 8. Y goes from 0 to what? So what's the upper bound on Y? What is it? 16. Right, so we need Y as a function of X. Over X. This would be how we divide the integral, right? We have to split it over the 2 regions, integrate X squared over both of those regions, and add the results. Because we chose to go vertically simple, dA is dy dx. So there is our double integral. Now to evaluate it. Neither of them have y. And that makes the dy easy. Length 0 to x is just x. Length 0 to 16 over x is just 16 over x. Antiderivative for x cubed.
That's what the.
That's going to go from x equals 0 to 4. Antiderivative for 16x. That's going to go from x equals 4 to 8. 4 to the 4th over 4 is 4 cubed. What is 4 cubed? Yes, 64. What is 8 squared?
64.
4 squared?
16.
64 minus 16.
Forty-eight.
48. 8 times 48. What's 8 times 50? What is it? Shouldn't be 38, is it?
284.
304.
I agree with 384. Right, 8 times 50 is 400 minus 16. And then 384 and 64 is 448. There is the integral. Now, I haven't shown it yet, right? This thing is so annoying. So let's show how we should evaluate a double integral like this in Mathematica. You are still going to have to, as far as I'm aware, set up the iterated integral. Integrate the function. I believe the order is outer. So x goes from 0 to 4, comma the inner. Y is going to go from 0 to x for that one, right? Plus, then the other one, x goes from 4 to 8, y 0 to 16 over x. 448. But you could also do a iterated, or you could also do this. Right, nest your integrals. like the other one. Both of them were. Just do that one, that one should be 64. That's what we got. So you can do either one. Just remember, if you're doing a single integrate command, it's the opposite order. Right? You put your outer variable first, then your inner variable. Go. So we want to evaluate this iterated integral. What do we have to integrate with respect to first? What is the antiderivative of e to the x squared?
X squared.
That's the derivative.
Isn't it the natural one?
It's like that one. You do X squared over X squared.
There is none. E to the x squared does not have an antiderivative. So what's an antiderivative? Function whose derivative is e to the x squared. There is no function that has a derivative e to the x squared.
Except you do X squared.
Derivative e to the x squared is 2x e to the x squared. All right, you should remember that from Calc 2 when you had to do numerical integration techniques. And you had to do that for integrals that didn't have an antiderivative, because the vast majority of functions do not have an antiderivative. Unlike derivatives. Right? Integration is actually very hard. But we could integrate that with respect to y. So why not switch the order? To switch the order, we're going to have to first visualize the region so we can actually find the right way of describing it. So here's where I'm going to use a command region plot. Right, the outer bounds are for x, and that said x went from 0 to 1. I'm sorry, outer bounds are for y, not x. I don't want comma. Double ampersand. And x went from 3y to 3. Now we just need ranges for X and Y. That is technically all we need. And if we can go ahead and execute, something's wrong. Why does it not like that? Oh, it's down there, that's why. Okay. Right, again, just ignore this little piece here. That's just a quirk with Mathematica because I'm further out than I need to be. When I shrink this, it'll be right. Turn off the frame. Turn on the axes. See, that looks better. This is no longer framed. Let's shorten this. It looks like I'll need to go and there, see, now it's corrected. So it's just a quirk with Mathematica. Boundary style are the lines, like the boundary of the region. And then in this case, the plot style itself is the shaded region. So if I just turn off the plot style, it takes away the shade. Or I could just do this, make it gray or light gray, something like that. I just get an idea of what the region is. So there is our region. I can edit things too, by the way, in Mathematica, which is actually what I'm going to do. So I'm going to switch this back to none. So I'm going to need to lower this magnification. Double click it. And so notice how if you just click it once, your outline is orange. Double click it, turns gray, means now you're in editing mode. Bless you. So I can add stuff to it. I actually just want to put it down here first. If I come up here to, you can't see it. There is an option up top that says palettes and then writing assistant. So that's what I'm going to click. And it won't show you that window because of the way that I have this set up. Can I add that window? Oh, not window, sorry. It was really bad. This is what I'm choosing. Oh no, it's not giving me that option, is it? What I have to do is switch to this. That's the one I really want then. So palettes up here, writing assistant. And bring brings this up. This allows us to do several things, typesetting. One of them, this is actually what I want. I want to come over here, I'm going to use script D. Script letters, capital D. So I can now copy that, double click that, and paste. That's actually not what I don't want to change the size. Close out of special characters, come up to here, let's change the size. Funny, looks good. I can move that in there. Well, there's my region D. What's this line?
My apologies.
But what's the equation of the line?
We really A squared is B squared.
X equals 3y. It's just from the bound. That has to be the line x equals 3y. Right, because what is x doing? X is going from that line, 3y, over to 3. So let's add that in here. You're actually going to keep the double equals. Okay, well, why not? Let's do this. And again, let's change that size, make it more visible. Something like that. And that's how you can edit a graphic within Mathematica. You cannot do that on the cloud version, though. You can only do that on the desktop version. Convert it to bitmap so I can copy and paste it. Right now, this is the description we have. But that was for horizontally simple, right? We want to write it vertically simple. So you have a vertical bar. What does that vertical bar slide across? Zero to what? 0 to 3, right? Now, as we slide the bar from 0 to 3, what does it extend along? What is it?
X over J.
Is that upper or lower?
Up or down?
What about the lower?
Oh, 0 to 3.
0, right, to x over 3. There's your description for vertically simple. Same region, just described two different ways. Fubini's theorem then says that these two iterated integrals are the same.
I had a question.
You answered it? Good. Right? Well, if we integrate now with respect to y first, it's just going to be x over 3, right? As the integral. Oh. But x over 3 times e to the x squared has an antiderivative. That's a u sub problem. Derivative of x squared is 2x. We have an x, we don't have a 2, so we're going to multiply the result by 1/6. And the antiderivative of e to the u is e to the u. E to the 9th minus 1 all over 6. This is called switching the order of integration, changing the order of integration. All you're really doing is changing the description of the region. And notice that by changing the description, right, going from horizontally to vertically, the integral became doable. I'm fairly certain if you tried to type that into your calculator, it would give you an error. Which would tell you have to try and switch the order. Set up a double integral to evaluate the volume of the solid under the graph of 22 minus x squared minus y squared and above the plane z equals 6. I believe I mentioned it, but whenever I do any kind of 3D plotting, I always just use the contour plot 3D instead of plot 3D. Because plot 3D just has funky things that it does. We need to plot two things. Z equals 22 minus x squared minus y squared, and z equals 6. Right? Let's just do minus 10 to 10. Except for Z, we'll go 0 to 10. See how that works. I don't think it's going to be high enough, but we'll see. Is there anything else like an axis or an axis label? Yeah, definitely go high enough on the Z, so let's up the Z to what, 15? That's fine. No, it's still not high enough. I think I have to go up to 22. Yeah. I could switch, I could actually lower the X and Y. I think I'll do that, -5 to 5. And maybe set the viewpoint. Right, so that now has it so that the x-axis coming out at us. From here, I can adjust it just a little bit. Let's just a tiny bit. Maybe do something like that. Oh, so right, so we just want to set up the double integral to evaluate the volume of the solid. Right, that's under this kind of paraboloid looking thing, but above this blue plane. Well, volume. How do you find volume as a double integral? Remember?
Is it 1 over the area?
That's average value. So be that, right? Upper function minus lower function, you integrate over some domain. The question is, what is the domain? What's the domain of integration? Wouldn't it just be this circle? It's the curve of intersection between the paraboloid and the plane, which is a circle. Six equals 22 minus x squared minus y squared. X squared plus y squared equals 16. So you want to describe that circle as vertically simple or horizontally simple? So you want to do horizontally, you want to do dx dy? Where would y go from? Remember, we're describing that circular region, because that is the domain of integration. What's the radius of the circle? Y would go -4 to +4. What about x? Goes from the lower semicircle, or I'm sorry, the left semicircle to the right semicircle. Negative root 16 minus y squared to positive root 16 minus y squared. That would be your volume. Go ahead and do that by hand. That's going to be really fun. It is doable. There's going to be a lot of algebra. Oh, but what do you notice about that region? It's clearly circular. What coordinate system should you think of? Do you think circle? Well, that's sphere. If you have a sphere, I'd agree spherical.
Cylindrical.
That would be for 3-dimensional. You just have 2-dimensional. So what is it? Polar! Why not convert this into polar coordinates and then integrate? Which is precisely what we look at next. Yes, you can do that in Cartesian and rectangular. That is possible. It won't always be possible to do it in rectangular coordinates. you may have to change your coordinate system. There are three common coordinate systems, right? Polar for two-dimensional, and then you have the two for three, cylindrical and spherical. However, in theory, there's an infinite number of coordinate systems you can use by making use of what's known as the Jacobian, which sadly I do not have enough time to cover this semester. But it is in your textbook, so I would recommend you read that section. It should be the last section of this chapter. And I think this is what, chapter 5 in the text. So last section of chapter 5 is about the Jacobian. It is essentially the change of variable equivalent for single integration. Again, we will only study one change of variable in double integration, and that's converting to polar. All right, let's say we have a polar region. All right, so polar region D. Integrating your function over the polar region, dA, the integral from alpha to beta of the integral, h1 of theta to h2 of theta, of your function, but now notice what dA becomes. It's not dr d theta, it's r dr d theta. So what do you think the most common mistake is when switching to polar? Forgetting that R. Smart. Immediately writing it down. Do not forget the R. Right, so in rectangular, dA is dy dx, right, or dx dy. In polar, dA is r dr d theta, or r d theta dr. Right, again, that order doesn't matter. Bless you. I guess you could consider this to be Fubini's theorem in polar coordinates. You're still going to make me do that. Okay, copy. And let's call this now question 0. Right, so let's go back to that and now evaluate that in polar coordinates, because that's going to be a lot easier to do. And if you're really up to the challenge, go ahead and evaluate that in rectangular and confirm that you get the exact same value. Again, that is doable, but it is going to require a bit of algebra, and I believe it's going to require trig sub from Calc 2. So let's just copy this one. So I don't have to rewrite it. So we now want to write this in polar. Outer integral, generally speaking, and how I will always keep it, outer integral is d theta. So bounds for theta. Right. If we look at a circle, you rotate your radius around an entire circle. What's your angle rotating through? From what to what?
0 to 2 pi.
0 to pi. Right now, for a circle, and it's not actually a circle, right? It's actually a disk, because the disk includes the region inside as well. What does your radius go from?
0 to 4.
For this one, 4, but 0 to whatever the radius happens to be, right? We now have to convert the integrand into a polar function. So how would you write 16 minus x squared minus y squared as a polar function?
16 minus r square root of
16 minus r
square.
squared. Right, remember r is the square root of x squared plus y squared. Now, your dx dy is your dA. So what does dA become in polar? R dr d theta. Until you get the hang of it, I would recommend using those steps in that order. As you get more comfortable, you can actually just incorporate the r and say, oh, the integrand is going to be 16r minus r cubed, and then dr d theta. Right, but until you really get the hang of it, just do it one step at a time. The integrand was 16 minus x squared minus y squared, so what is that now? 16 minus r squared. Then what is dA? R dr d theta. There is the conversion. Look at the integrand. Do you see a theta anywhere? Look on the bounds for r. Is r dependent on theta? No. Oh, cool. Then integral of d theta from 0 to pi is just 2 pi. Because again, remember, the order in which you integrate does not matter. In fact, this is what we would call a rectangular polar region. Right? This is a polar rectangle. Because both your bounds are constants, right? Like if you have the rectangle 0 to 4 cross 0 to 4, that means x goes from 0 to 4 to y goes from 0 to 4. Your bounds are constant. This is a polar rectangle. Those are the easiest types of regions to integrate. What is our antiderivative? That goes from 0 to 4. 2 pi. Alright, so 4 squared Let's do it this way. 4 squared, that's going to be 2 to the 4th times 2 cubed is 2 to the 7th. What is 2 to the 7th? Then you get r to the 4th over 4, which is 4 cubed, which is what? What's 128 minus 64? And now double that, goes back to 128. There's your volume, 128 pi. See that? So now not only do you have to check your order of integration, right, because as we saw previously, what was it? It was here. That order was impossible to do, so we had to switch the order. You now also have to keep track of your coordinate system. You may not be able to do it in a specific coordinate system, so you have to change it. Also, as in this example, it might also be easier in a different coordinate system. Right? So yes, we set this up in rectangular, but it's actually easier to do it in polar. So we want to set this integral up when you evaluate this integral. Well, before we even try to describe the region, x squared plus y squared to the 3 halves that has no antiderivative in rectangular. I'm sorry, this cannot even be done in rectangular coordinates. We have to convert this. But if you look at the region, that's clearly easier in polar than in rectangular. So when we set up a description for the region, we're going to define it as a polar region, r theta. What is theta going to go from? Again, this is a disk, so this is a really easy one to describe. Other way around, 0 to 2 pi. By the way, that's not the only correct answer. Could have gone pi over 2 to 5 pi over 2. And any interval that is a length of 2 pi would work. This is just the standard 0 to 2 pi, so that's what we're going to stick with. What about the radius, r? The integrand is x squared plus y squared to the 3 halves. Write that as a polar expression. Yes, I saw the smirk. Polar expression. A little too early for Christmas. Was a good movie though. So what is that in polar? I think you may have jumped ahead.
Yeah, I was doing something on this.
Don't simplify, I just want the
Oh, yeah.
integrate for right now,
R squared to
which is what?
R, so
Just R cubed? Now what is dA?
R dr.
Right, I'm always going to break it down this way, just so you can clearly see that we're going to have an extra R. Right, now simplify. Right, so we are going to have R to the fourth dr d theta. Oh, well, once again, the integrand has no theta in it. Our R is independent of theta. So just integrate with respect to theta first, 2 pi. What is the antiderivative?
R
R goes from 0 to 6. What is 6 to the 5th power? And then doubled.
$15,552.
15,552. Don't even try to do that in your head. I actually don't know what 6 to the 5th power is off the top of my head. It's 2 to the 5th times 3 to the 5th. I know that. I know 2 to the 5th. I actually do know 3 to the 5th. And of course, that's not divisible by 5, so that can't be simplified any further. That would be your integral. Again, look how easy that was in Poland. So as we've been seeing, setting up the integral is difficult. Right? You have to actually describe the region. But the actual evaluation generally isn't iterative. You may get the case where, yes, you're going to have to do some Calc 2 techniques. But for the most part, evaluating the integrals is not going to be your challenging part. It's going to be setting up your integral as an iterated integral. Right, so practice, practice, practice. Look at several different regions and try to describe them. See if you can set them up the right way, at the very least. Any questions from today? So I believe I did misspeak. Definitely was not having a good day on Tuesday. Made a lot of mistakes. The exam is next Friday. So the second exam is on the 4th, which is next Friday. Not 2 Fridays from now. Project 4, I may have forgotten to mention that. I think that went up by last class, but either way, Project 4 is up there. It has to do with the volumes of hyperspheres, which is pretty cool. That will be due on the 11th, as usual. Different groups, so make sure you go on and you check your group on campus. And the website homework on Polar did go up, but it won't be due until next Friday. We will finish up with Polar integration tomorrow. The Phillies lose, I'm deducting 30 points from everyone.
Wait, they're not gonna lose? Wait, did the Earth start movies?
Today's opening day.
Oh, okay. Where's the plan?